All right, so today we're going to be talking about ethanol sealing challenges solved, taking a system approach to sealing and how we improve asset uptime in these difficult to seal processes. I'm Terry Roberts, the Midwest Regional Manager for SEPCO Sealing Equipment Products down in Alabaster, Alabama. I've been in the fluid sealing industry for 22 years. I provide sales support, training, troubleshooting, hands-on installations and things like that in the field with our distributors and end users. And I'm also on the technical committee of the ISD, International Sealing Distributors. And here's a picture of me at one of these ethanol plants I was recently at. So kind of get started into the agenda today is going to cover the ethanol process, how ethanol is produced, what sealing challenges are involved with producing the ethanol. We'll focus on the evaporator pumps, which basically gives us the syrup product, the value of mechanical seal failure analysis, and the solution that we provided to this specific plant. Before we get started, we'd like to do a little poll here and see, out of our current attendees, who is currently working in or has worked in the ethanol industry. So we're going to start by going through the ethanol process step by step, kind of a condensed version, which includes milling, liquefaction, fermentation, distillation, evaporation, denaturation. It starts by the milling process, which a grain is selected. In this case, it's corn. Most of these ethanol plants are corn. The grain is selected and ground into a meal or flour. Then it goes to a process where they add water to it to make a slurry, which is called mash. That mash is cooked, and adding enzymes, the starch molecules are broken down into glucose, which are simple sugars. From there, the mash is pumped over to the fermenter tanks, where yeast is added. Yeast is added to consume the simple sugars, and during that process, the beer releases CO2 and converts the sugars into ethanol. That resulting product there is beer, which is 17 to 18% ethanol at that point. From there, it's then pumped into the distillation columns, where we're trying to achieve 100% ethanol. To achieve that, we must separate the ethanol molecules from the water and the solids, or the liquid and solids that are present in the beer. And they do that by applying heat. And since ethanol evaporates at a lower temperature than the water does, the ethanol vaporizes, rises to the top of the columns there that you see down in that picture below, goes up through that piping, where it'll move to the next one and get the next column and get distilled again. And from there, we separate all of the water, well, most of the water out. And after distillation, we end up with 95% ethanol, which is 190 proof. It will go from there through a molecular sieve, which will remove the remaining 5% of the water, which now gets us to 100% ethanol, or 200 proof. From there, it will go to the denaturant process, which adds about 2% of gasoline to the ethanol to make it undrinkable. So it is an alcohol that can be consumed at that point, but they add a little bit of gasoline to there to make it undrinkable. And then from there, it'll go to storage tanks, where it'll be loaded onto rail car, barges, or trucks to go out to market. The ethanol process and where the sealing challenges are. Although there are seal failures throughout the entire process of making ethanol, the lion's share occurred at this plant during the evaporation process. So what happens is, after distillation, the solids and liquids that are left over from the ethanol being removed, the solids and liquids left over, which is called whole stillage, goes through a process of removing those liquids to get us back to the solids, which is DDGs, which are dry distiller grains, which is a high protein animal feed. So this is the part of the corn that's unused during the ethanol making process that goes back to the market and gets sold to the farmers for their livestock feed and so forth. This one particular plant, we were dealing directly with a plant engineer. It was struggling with seal failures, specifically in this evaporation process, the evaporator pumps, where they were trying to remove those solids. In addition to those problems, the engineer had other problems, which were detecting inboard seal failures and proper training of his maintenance team. So we wanted to go in and address all of these problems to help them fix those problems, but also train these maintenance guys to make sure that moving forward we didn't have these issues on other applications. The engineer struggled daily with these failures because the slurry flowing through the pumps had many challenges. The fluid being pumped there, as the stillage is pumped from one stage to the next through these evaporator pumps, it's heated up, removing the water, which makes the product hot, abrasive, thick, sticky. And again, as it moves from one stage to the next in this evaporation process, it gets thicker and thicker. So it becomes a lot harder to seal. So it's hot and sticky and thick and very hard to get these seals to last if it's not properly set up. The underlying pump system issues were exacerbated by the difficult to handle fluid. This included improper pump installation, improper seal installation, pump misalignment, and improper environmental controls. So we had to address all of those issues. So the mechanical seal is always the failure. The mechanical seal is always what shows up as the failure. But is it true or false that the mechanical seal is always the reason for this failure? The answer to that question is really false. Most failures are caused by systematic problems, or true. So there we go. So we got 6 false and 1 true. Good. So it is false, and the reason is most seal failures are due to some kind of problem in the system, whether it's operations or setup or something like that, that causes that seal to fail. The problem with the seal was the weak link in the system, and it shows that failure before anything else does. So when people think they have bad seals or seal issues, changing another seal or another manufacturer's seal into that same pump without changing anything that's causing those failures is not going to change anything with the way that seal or that pump is running, or the reliability of that pump. So now that we know the seal failed, we have to figure out why. The only way to really find out why those seals are failing is to do an in-depth failure analysis. We had to do an in-depth failure analysis to find out what factors are causing that mechanical seal to leak. Again, the mechanical seal is going to show the failure, it's going to show the leakage, but it's not necessarily the seal's fault. The seal is like a book. It'll tell you a story if you let it. There are hundreds of variables that contribute to a mechanical seal failure. If you diagnose the reason the specific seal failed, you'll learn how to prevent it from occurring again. Seals fail for one of 3 reasons. It's either application, operations, or installation. So by doing this failure analysis on these seals, we can see over to the right there, was the right seal selected for the application? Are the operating conditions optimized? Did the team set up the flush system properly, and is the barrier fluid performing effectively? So we have to look at each of those areas, again, application, operation, installation, and find out exactly what's causing those seals to fail in order to get those fixed. At this specific plant, there were 3 problems identified by doing an analysis on a seal that had come out of there. The wrong seal design was being used. The environmental controls were not effective and that they were not set up properly. And a more robust barrier fluid was needed. Flushing with water or glycol water is not going to work in this application. So as you can see, 3 of the 4 highlighted there, 3 of the 4 that we look at contributing factors were present in this analysis and helped us kind of determine what was going on. so that we could fix that problem moving forward. So again, back to the systems approach. The new seal design was selected, and it was a balanced seal, integral pumping ring, tangential flush ports. Next, we looked at the barrier fluid, and we designed or implemented a barrier fluid that was specially formulated for the application handling, capable of handling the elevated temperatures. And then a new convection tank or seal pot was installed, and setup and position were changed. So now we'll go into each of those components separately. First part we looked at was the mechanical seal design. We went with a dual seal design, dual cartridge seal design. The balanced design allowed us to run a little higher flush pressure. They weren't running high enough flush pressure to the seal pot. So that was one of the things we changed, but the concern was as the product gets thick, and sticky, it starts to build up on the piping, which potentially can cause a deadhead condition. In that case, the barrier or the product will start to back up towards the mechanical seal and raise the pressure on the mechanical seal product side. So we had to have a higher flush pressure on the seal pot and the barrier fluid to make sure to keep that product out of our seal faces and out of in between that seal cavity and into our barrier fluid closed loop system. Integral pumping ring in the seal has helped to move the barrier fluid to the tank for cooling. So that pumping ring in there adds some energy, some turbulence to that liquid in between there, the barrier fluid, with that heat that's causing it to rise up to that seal pot to cool. The pumping ring aids in helping to move that barrier fluid out of that seal in between those seal faces and the gland. And then the tangential flush connections provided more effective cooling in the seal gland. So as you can see, our seal connections, the flush ports up at the top of that seal, are together. And what that allows is us to get 360-degree coverage inside of that seal, or movement inside of that seal, as opposed to the design they were currently using or previously using, where the connections were at 180 degrees apart. And not only that, they were running them in at 3 and out at 9 o'clock, which was allowing a lot of heat to get trapped up in the top of that seal gland. So by doing these tangential connections, we're going in and out and basically getting 360-degree coverage with the barrier fluid. Next, we wanted to look at the barrier fluid. They were using glycol and water. They were using the wrong glycol, and that glycol and water mix was not sufficient to handle the heat that was generated between the process and the mechanical seal generated heat. So we went in with a high-performance synthetic oil, specifically formulated to handle those heat and oxidation and things like that. So it's FDA compliant, contains no detergents or heavy metals, resists thermal and oxidative degradation. So it's capable of handling those high temperatures we need. Excellent heat transfer, and it provides a lot longer seal life. So by changing to that better barrier fluid, we were not breaking down and allowing for good lubrication and cooling to the seal faces. Next, we looked at the convection tank or the seal pot. The seal pot that was in there, after many failures, had a lot of contamination build up in it. So just going in and cleaning that out with hot water or something, which is what they were trying to do, was not breaking down the stuff that was building up inside the seal pot. So they tried to steam it and still couldn't get it all out of there. So we just went in with a brand new seal pot. Ours also had integral cooling coils. So if the temperatures get too high, we can put chilled water through those cooling coils to lower the temperature before it gets circulated back to the seal as well. But the convection tank with proper barrier fluid is essential in these applications where you got high temperatures and things like that. So the closed loop system allows the fluid to travel back to the tank for cooling, or go to the tank for cooling and then back to the mechanical seal to provide lubrication for the seal faces. This tank and the following training on setup helped further make improvements. What we did there was we put the tank on the correct side of the pump, located it within the correct distances from the center line of the shaft up 12 to 30 inches, no more than 4 feet away. The seal pot was about 8 feet away from this pump. So in order for convection with no pumping ring to happen, there was no way it could get enough energy in the fluid to convect all the way to the seal pot, which was close to 8 feet away from that pump. So by changing the location of that also helped us to more effectively thermosiphon. So by using the proper location and the proper piping, proper thermosiphoning was able to take place. So here's one example of one that we set up on this pump. You can see by the arrows there the correct tank relative to the pump, filled with the new barrier fluid that we put in. In this case, the pump from the motor end, viewed from the motor end, is rotating clockwise. So we put our seal connections on the 3 o'clock position, or on the right side there, as you see. We want to go in from the bottom of the seal pot where the fluid is the coolest to siphon into the seal at the bottom of the mechanical seal. And as it goes around with the rotation of the pump, and the pumping ring will get circulated 360 degrees back to that top connection, which then goes back up to the seal pot at a higher location in that pot. And what that does allows that heated fluid to rise where it can rest and cool, and then it'll kind of slowly circulate back to the bottom and get sent back to the mechanical seal. So that closed loop system with the proper barrier fluid and such allows this fluid to go up and cool and circulate and lubricate without breaking down. And then the mechanical seal down at the bottom there, mechanical seal installed properly. One thing that we did find as well, where they were making impeller adjustments after the seal was set. So by handling this training, or going over this training on the actual installation of the seal, was very valuable as well. So the result of this pilot installation led to a full conversion of this plant, but other seals being installed using the same methods. And it all started by doing a failure analysis on seals that had failed, that had previously been running in those pumps. So in this case, the MTBR, mean time between replacements on that seal, they were getting roughly 2 to 3 months out of there, out of each seal, and they were pulling that pump to replace it. We are up to 24 months currently and still running in that pump. So we have drastically or dramatically increased the reliability of that pump. And going back and following up with this engineer, we wanted to follow up with him, to look at other things, see what he needed from us, and get some statements on what he thought was different about what we were doing compared to the other seal suppliers or manufacturers that had been in this plant in the past. And a couple of the statements we got from him, one was the failure analysis reports had been valuable feedback to the maintenance team. We thoroughly discussed these reports. They're very detailed. Every component of the seal was broken down, inspected, measured, and a full detailed report is supplied to these plants so they can see exactly what we see. We'll also give them some picture evidence to support the documentation so they can see exactly what was going on and what we found. And then there is the mode of failure, what caused that seal to fail. And then we also give them a suggested corrective action. And what that is, that's telling them we see misalignment here, severe misalignment. And if you're laser aligning your pump, maybe we need to go to the wet end of the pump and unbolt or unflange the loop. Start looking for pipe strain, bolt binding, saw foot. Pipe support has been another one that we found a lot lately. These products with the discharge going straight up 10, 15, 20 feet in the air with decent sized pipes on there that are full of product is very heavy pushing down on that casing or on that volute. So that product pushing on there is putting a strain or a bind on that casing, along with the saw foot and bolt binding and things like that we need to go in and eliminate in order to get those stresses and strains off of that casing to make sure that our mechanical seal still runs in the center or concentric to the stuffing box. So the failure analysis reports, he says, have been very, very valuable to them, and they all go through them as a team every time we send one in on a seal that has come out of that pump. or any pump in that plant, sorry. Another statement he made was the proper training of the maintenance team is immensely valuable. There are aspects of mechanical seals that aren't necessarily intuitive to the installing team. Don't underestimate how much each mechanic understands about seals. When you go into these plants, most people, or most of these mechanics they've learned to install mechanical seals from someone that was in there previously that showed them. So to have a manufacturer to come in and show them exactly how these seals work so that they understand the seal components and what each does and how it operates, then they'll understand the importance of the installation procedures that are put in place with these seals. So what we've done is we put these in steps, the installation steps. We go into the plant and we go through these one by one with these guys. What we did first was a classroom training and going through these slides and talking about all of these installation instructions and proper procedures and things like that. So as we come into the plant and do that initially, they haven't really had much, I guess, history or experience with our product specifically. So by coming back and helping them do an actual install after they decide they want to move forward with these solutions, coming back and doing a hands-on training in the shop, and then taking the pump out and actually working with them to install the seals, the seal pots, getting everything set up and operated properly. We have, he basically said that no one else has done that for them before. And we find that a lot out there. So proper training is huge for these plants. So taking this systems approach is absolutely vital to fixing these seal problems and keeping that business for yourself. We're not trying to go in there and just change mechanical seals or manufacturers. We have to take a systems approach and find out exactly what's going on. So the failure analysis and the training are vital to the success and the reliability of these pumps and these plants.
Thank you, Terry. But I actually have a couple questions for you, Terry.
Absolutely.
One is, what are the other industries outside of ethanol that this system would work for?
Yeah, so anywhere that we have high temperatures, processing plants where you're going to have high temperatures, elevated temperatures we consider to be anything over about 170 degrees. A lot of people are using water as a barrier fluid, and water does not lubricate once you get above about 160 or 170 degrees F. So therefore, the seal pot with the closed loop system with a synthetic oil barrier fluid with a flash point. The flash point on this particular fluid was 460 degrees F. So when you get into temperatures that are over about 170, 180, if you're not going to run chilled water through your cooling coils to cool that water down as it sits in the seal pot to rest before it gets circulated back to your seal, then that's going to break down that barrier fluid. So if you don't have chilled water available, or a plant isn't willing to run the chilled water to the cooling coils to cool that down, this setup can be used in anything where your temperatures are higher than, again, about 160 or 170 F because of that heat from the process and the heat generated by your mechanical seal faces.
Okay, that's awesome. To be able to use it in ethanol production is definitely great, but to know that you can use it in other industries is also really good to kind of look into and see if it could potentially work for them.
Yes, absolutely. We use that in chemical plants, ethanol distilleries, any processing plant where the temperatures are over 160 or 170 F, we would use this system.
So from your experience, what are some other installation issues that you've seen in regards to the compounding of sealing with mechanical seals?
Alignment seems to be the biggest issue, misalignment, I should say. Almost all plants that we go into these days are using laser aligners, laser alignment equipment that are aligning the pump motor the motor to the pump through the coupling. The advantage of using a back pull-out pump is that you don't have to unbolt the piping, the flanges and the piping. So your product piping and your suction and your discharge piping and the volute can all stay in place. So when that stuff gets, especially in ethanol, but it happens all over, when they build these plants, the piping is prefabbed and they run it, and then they'll pour the bases and mount the pumps, and then the piping is prefabbed. So wherever it comes down to the pump or comes to mate up to the pump, there's a huge issue with that not meeting properly or mating properly. So therefore, instead of cutting that piping and changing that, they apply a lot of pressure, come-alongs, power packs, things like that, ratchet straps to manipulate the pump to the piping to bolt it. And as soon as you take those things off of there, it puts a tremendous strain on the casing, which takes the shaft out. It's no longer concentric to the stuffing box. It puts some tweak or binding on there, and you lose clearances inside the seal chamber. And you also, when you mount a mechanical seal, the gland mounts to the stuffing box, which follows that piping part, and the rotating part of the seal goes where wherever the shaft goes. So if you have shaft running through and casing here and it's supposed to be perpendicular, if you start putting any tweaking or binding on there, that's going to misalign the internal or rotating parts of the seal with the stationary parts.
Yeah, and that's not good.
No, that is not good. When you lose clearances, it's something rotating at 1800 or 3600 RPM, metal against metal that's not moving. So not good. Creates a lot of heat, creates a lot of issues, wear, friction, heat, all of that contributes to, again, more elevated temperatures in that barrier fluid as well, because that will transfer through.
Now, you had mentioned about being able to actually come and train people how to properly install. Can you give a little information on how people can learn about that and potentially get that service from you?
Yes, absolutely. So my contact information is there on the screen. I'm the Midwest Regional Manager, so I cover 14 states in the Midwest. We also have guys in the Northeast, the Mid-Atlantic, Southeast, down in Texas, and so forth. So if someone wants to contact me and they're in my area, I would handle that training with them. If not, I could put them in touch with the other people at our company to get them set up with them to do training as well.
Awesome. I think that's definitely needed, especially in our industry and with newer people coming in, to be able to have that technical expertise from experts like yourself to really show them the correct ways to be doing things, and then they can continue to teach in their plants and facilities once they know what they're supposed to be doing.
Sure. Yeah, we had an ISD, International Sealing Distributor Technical Committee. We had a meeting there, and one of the biggest concerns with the whole group, which were people from all across the U.S., was the aging workforce leaving and the experience leaving with them. So the lack of experience with the younger generation coming into, there's a huge gap in that experience for as far as installation and how these products work and so forth. So.
Yes, 100%. And because of that, we need to have people like yourself and other thought leaders in the industry that are able to teach those upcoming generations the skills that they need to be successful, since those generations that are on their way out might not necessarily be able to teach them what they need to know. So that's wonderful to know that you guys are doing that and have those resources.
Yes.
Alrighty, well, I think that is a close for today. Terry, thank you so much for your time and your expertise on this subject.
Thank you for your time.
Thank you.